Greetings. All right. Our goal today, try to figure out related rates. Woo, hard stuff. Um, had a discussion with my 8 o'clock class. I'm just about feeling pretty overwhelmed with all of this, and in light of some people are taking physics. This topic is hard, and et cetera, et cetera. And I moved the quiz that you owe me, the take home quiz. There's no reason that couldn't be due tomorrow instead of today. I just need time to grade it because Monday we're going to be reviewing, and I want you to have it in your hand Monday so that you can learn from it. If this is a normal physical class, I'd be handing it back to you in class Monday so that you had time to look at it and then time to take the test on Tuesday. But there's no reason you couldn't give me that quiz Friday night instead of tonight, just to give you a little bit extra time based on your other classes. But the only thing I would say is, this piles up. I mean, it depends. You got a lot of you have other things going on in your life. You've got maybe a job, you're taking other hard classes and so forth. But ideally, you should already be done with everything in that quiz except for the last two questions. Or you're kind of behind. You're making this way harder for yourself than you should. If that's out of laziness, then tough on you. Fine. But if you got a job and maybe you have a house, you got to mow the dumb lawn, and community college, you get all kinds of different kind of levels of where people are in their lives. That's what community college is a chance to go back and get some of that stuff. But ideally, you're done with everything except for the 3.11 assignment in My Open Math, because we're working on that right now, and you're done with all of that quiz except for the last couple of questions, which I'm going to help you get better at right now. But as much as I can, I want to give you as much time as I possibly can. So yeah, no reason. I changed that in My Open Math, but you can give that to me Friday night, and I still have time to get it graded. It takes me forever to grade that stuff, but I still have time to get it graded and give it back to you. All right, so let's get better at this. I mean, I need to show you a bunch more examples. We could spend a week on this and probably still be getting better the whole time. So, related rates. So let's say we got this crane out here that is kind of lifting up a box, maybe out of a ship or something like that. And in order for that crane to be able to lift that up, it has to have some kind of maybe a cable hooked to it up higher. And to keep it simple, I think I'll say there's the attachment point. And say the cable connects right up here. And so there's this triangle. And in reality, this cable kind of goes over a pulley and comes down here around and winds around a winch. And that winch is actually going to either open up and kind of let the box drop down, or it's going to wind it up and lift the box up in the air. So there's kind of two different options for kind of how that might work. But I want you just to stare at that triangle for a second and think that, okay, the cable, let's say the cable is pulling the box, pulling it in. So it's trying to lift the box higher in the air. It's pulling it in. And if you just look at the triangle for a second, defined by kind of these, oh, that wasn't good. Defined by kind of these 3 points right here. Which parts of that triangle are changing and which parts are staying the same, if you understand the drawing that I gave? Does it make sense that This distance would stay the same. Maybe I'll make it 14 meters long. That attachment point where the cable is attached to the boom and how far that is away from kind of the hinge or the pivot point, that's not changing. And this length up here is not changing either. Let's see, to make it at least look reasonably to scale. Let's say that looks like 10 meters. That's not changing. But this length up here would be changing, wouldn't it? So I'll call it L for length. I mean, that's the concept of a variable and a constant. L's getting, well, in this case, shorter. L's getting shorter because we said the cable is getting pulled in because the operator's lifting the box up in the air. And as a consequence of that, isn't this angle down here also changing? So I got to give that a letter name too, the variable, because it varies. And so the concept of related rates are, would you agree that in the language of calculus, dl dt, or how fast the cable is getting pulled in, is related to d theta dt, which is how fast that angle, if you will, is closing up? Those two rates would be related to each other. If you pull the cable in really fast, dl dt, if that's getting pulled in really fast, then d theta dt is going to be closing really fast too. If the cable's getting pulled in really slow, then the angle is going to close really slow. These two things would be related to each other. And so, just to kind of simplify the picture a little bit, if I told you that this cable was being pulled in by a winch at, let's make it pulled in kind of fast, just so that it makes the angle look a little bit better. But let's say it's getting pulled in at 32 meters a second. Do you understand that that's code for, oh, dl dt is 32 meters a second? And I don't mean this to be tricky, but in this case it's pulling, so L's actually getting shorter, which means that would actually be negative 32 meters a second. L's getting smaller, it's not getting bigger.
Is any part of that triangle a 90-degree angle?
Yeah, it's a good question. Is any part of this 90 degrees? I'm going to erase this, but would you agree that all three of these angles are actually variables? They're all changing. If you pull that in, all those angles are changing. And so none of them are stuck at 90. And that's a good question to ask, Dale, because if one of them is 90, then I have Pythagorean theorem. I can use Pythagorean theorem in 90-degree triangles. I can use sine, cosine, and tangent in 90-degree triangles. But in this problem, this is particularly cool and terrifying because none of those are 90 degrees. And so how am I supposed to relate all this stuff if I don't know any equations that work? Well, again, let's kind of march down the process here. I need some equation that relates, or I'll just say with, it's going to have theta in it, and it's going to have L in it. It's going to have those two letters in it. Since I'm interested in not those letters themselves, but I'm interested in their speeds. So I need some equation where it's theta and L. This would ask a lot of your algebra knowledge. You'd have to be able to speak the language of algebra really well. Does anybody see an equation? Does anybody know of an equation that works for angles and triangles except for non-right triangles?
Doesn't the law of cosines work?
Yeah, there's the law of sines and the law of cosines. And I posted on my Open Math a trig review sheet, and we've been looking at the first page, but the second page shows the law of cosines and the law of sines. And in this particular case, I want the law of cosines because law of cosines involves only one angle. Law of sines involves two angles, and I don't have a reason to get a second angle involved here. Now, again, could you go up here and say this is angle alpha, and I'll get that angle involved too? You could, but you're going to just make your life harder. So I really would like to not have that angle involved. And also, so here's the equation. Law of cosines says that L squared equals 10 squared plus 14 squared. Thank God for constants. It looks just like the Pythagorean theorem. Now, how did I know to put L squared by itself? How come it isn't 10 that's over there by itself on one side? You got to dredge up your knowledge of the past here. But the formula goes on to say minus 2 times one side times the other side times the cosine. And it's very important that the cosine is the angle across from the one you chose to put by itself. And on my formula sheet, I said, this angle, this is over C over here, and this is cosine of C. So since I put L by itself, then it's the angle across from it that I'm taking the cosine of. That's how I knew to put L by itself and not 10 or 14. Now, we'll talk about this maybe a little bit more after class, but like this is probably the single hardest thing you've ever done, what we're learning right now, because you have to speak the language of algebra so well. Like you actually have to be able to look at this problem and go, oh yeah, law of cosines, I know that. I remember that. I know how that works. You got a shot at knowing that because it was the class right before this. I mean, in an ideal world, you took trig. Well, I guess this is fall, so you took trig last spring. But that's a tall order to still know that, to understand that you can't use just sine and cosine here because it's not a right triangle. It's asking a lot. The section is asking a lot. You have to know calculus really well. You have to know everything you've ever learned in math really well to find this section doable. So I guess I just want to say right now, cut yourself a little slack on this section. You're not walking in here knowing all that stuff really well. You got holes in your knowledge. This is tough. If you're taking this class because you want to be an engineer, well, I'm showing you a problem that's a kind of an engineering related problem right now. So you might be thinking, okay, good. Yeah, I can see why an engineer would need to know this stuff. But dentists have to take calculus too. Does a dentist need to know what we're talking about right now? I'd say no. Like you don't need to know this if you're a dentist, but they make dentists take calculus. If you're going to be a veterinarian, you got to take calculus. Some of you said, I like animals, I'm going to be a veterinarian. Do you need to know this to be a veterinarian? Not really. I'm not the one that dictates. I'm not the veterinary school, so I'm not the one telling you need to take this. But if you're in a degree that, you know, kind of needs the engineering physics stuff, then you probably think, yeah, cool. If you're not, you're probably suffering a lot. Well, you know, don't forget, C's get degrees, and a lot of people have to take calculus twice. And if you don't have enough time in your life right now to really devote to this so that you're caught up and spend the extra time you need to really get good at this stuff, it's like, I get that.
Doug, are we solving for L or for theta?
Yeah, now let's go figure this out. So, okay, great. We got this equation. Let's clean it up a little bit first. And speech. 10 squared is 100. 14 squared, I think, is 196. I forgot.
144.
196 plus 14 squared is 196 plus 100 is 296. So I could rewrite that as 296. And then 2 times 14 is 28 times 10 is 280. So that's as simple as I can get this. And you can't go 296 minus 280 and get 16. You should know that because of the order of operations. But this is the best I'm going to be able to do. Like, this is a good equation. I'm definitely going to need this. And in the language that I helped you with yesterday, I said, this is the static equation. This is what you would have done in a Math 112 class. If I said, okay, theta is 19 degrees, what is L? Like you could answer that. But I can't say theta is 19 degrees because if it's 19 degrees, then this is not moving. And we're talking about this thing being moving. So that's why the second part of these questions is, well, get it moving. Get moving. So let's take a derivative. So the derivative of L squared would be 2 times L times the derivative of L. That's chain rule. Derivative of 296, gone. Derivative of 280 times cosine of junk. The 280 comes along for the ride. The derivative of cosine of junk is negative sine of junk. That's kind of nice. I just changed that to a plus sign. But chain rule says times the derivative of the junk. You should feel pretty good about that. But again, we just learned that in the last couple of days, so maybe you don't feel that good about that. Neither one would surprise me right now. So why are we taking a derivative? Because this is a calculus class and that's what we do? No, because we or somebody is interested in how things are changing. And so that's why we need an equation with L's and thetas. And then that's why we had to take its derivative. So now we actually have, we now have the stuff that we're interested in finding. Now let me go back. If this was a problem in the book or a problem on a test, there would be a whole bunch of givens here. So let me sort of go back and build that from scratch. Like we're now ready to use that equation for things, but we don't know anything. Like you haven't told me anything. So let's say these are the kind of things that are, as I said, given from the start. So let's say our goal was to find d theta dt. So let's say the cable, well, we already know that. I'm just going to rewrite that. I already told you dl dt was negative 32 meters a second, so that's a given. But then the second thing we need is a snapshot in time. There'd actually be a second thing that would have to be given here. And I don't know what it is, but let's just say the snapshot in time is when L is equal to, let's say, well, it's going to go with the picture a little bit. Let's say it's 18 meters. That would be given. And the problem would be asking us to find something. In this case, we're finding d theta dt. We're trying to find how the angle is changing. How fast is the angle changing? And it is important to understand that this is the snapshot in time. And I say snapshot because you can't say L is 18. Do you understand that? If L is 18, then the crane's not moving and d theta dt is 0. The angle's not changing at all. That's why you have to understand that the problem will say something in English in your book assignment or on a test. It'll say find d theta dt when L is 18 meters, as opposed to just saying L is 18 meters. I don't know if the logic of that makes sense to you. This is a snapshot in time while the crane is actually moving. Okay, great. So really what you need to see down here is, look, I've got L as an unknown, I've got dl dt as an unknown, I've got theta as an unknown, and I've got d theta dt as an unknown. This is an algebra problem. And I was not very good in physics at understanding the logic of this. I've got an equation here with 4 unknowns. And so algebraically, if you tell me 3, then I can find the 4th. And of course, the problem was asking for this one, so I'm not going to know that. But basically, I need to know the other 3. Those are the other 3 ingredients I need. I'm going to have to be told those. Now, ideally, when I look back at the start of the problem, I hope they just said L is 6, dl dt is 9, and theta is 6. I hope they just told me all those and I could just go plug them in. Well, we did know some of those. We were told that L was 18, so I can throw 18 meters in there. We were told dl dt was negative 32 meters a second. But we weren't told theta. So is that an oversight? Was that supposed to be a given? And the answer is no. I can actually use the static equation to figure it out for myself. If I go back to the static equation and I throw in L is 18, then I can get theta myself. This is what it means to speak the language of algebra. And this is why physics is so hard, because you have like 40 equations. And it's like, how am I supposed to know which ones to use? Well, I circled those 2 just because I said, hey, here's 2 equations that I have that I can use to figure out what I want to know. And I'm going to need that static one now. So let's go figure that out. Let's see, 18 squared. 18 squared is 324. And so let's see, I'm going to subtract 296 from both sides. Again, don't think you can go 296 minus 280. You're screwing up the order of operations. So if I subtract 296 over, I get 28 equals negative 280. Don't do something stupid and add 280 to both sides. That's 280 times cosine. So you got to divide by 280. 28 divided by 280 is conveniently 0.1. We got lucky there. So I've got negative 0.1 equals cosine of theta. How do you solve for theta? Somebody remind us. What do I have to do to figure out what theta is then?
Get the
Inverse.
Yeah, the inverse cosine. Keep in mind, what I really want to know here is not even theta. I want to know the sine of theta. I'll talk about that in a minute. But if I bust out my machine now, it actually doesn't matter whether you're in degree or radian mode, but I'm in radian mode, and so fine. So I take the inverse cosine, second cosine of negative 0.1, and my calculator says you are at 1.67 radians. So theta is approximately 1.67. I'm just thinking out loud here, but let's see, what does that mean? Unit circle. I know right here I've memorized that's 1.57. So I'm apparently over here somewhere. I'm over there. In other words, my angle's like more than 90 degrees. Does that make sense? An angle is more than 90 degrees in this picture up here? Yeah, sure. Like my picture doesn't have it drawn at more than 90 degrees, but if this L up here being 18 was open wide enough, that's going to cause the angle to open up a little bit. And so, yeah, that's reasonable. I guess that makes sense. And so now that I know that I can throw it in here, is I can now kind of, that's an important number. I always draw a little cloud around numbers that are important after all this work I just did. Now I can go up here and kind of throw it in there. And now I got everything I need. I got the three unknowns I needed. And now I can just do the algebra, crunch the numbers to get d theta dt. So switch colors. So let's see, 2 times 18. So let's go solve this. Let's take a few steps. 2 times 18 times 32. 2 times 18 times 32. I get, and it's negative, I get negative 1152 equals 280 times the sine of 1.67 times d theta dt. So I just got to figure out what 280 times the sine of 1.67 is. 280 times the sine of 1.67 is about 278.6. And again, it's a good idea to tell everybody you're rounding. I rounded 1.67, so it's not equal anymore. It's just close. And I got positive 278.6. So then all I have to do is divide by 278.6. Negative 1152 divided by 278.6 is approximately 4.13. So d theta dt is approximately negative 4.1. What's the unit for that? Well, I know my times were in seconds, so it's something per second. What's on top?
Radians?
Yeah, well, it's theta, so it's either radians or degrees. It's some kind of an angle measurement, right? So that's kind of weird. Like we never even talked about it. I'm not going to do this. I'm not going to go into this because this is already hard enough. But if you go back in physics, all the numbers that I had in here, like this 280, for instance, that 280 was 2 times 10 meters times 14 meters. That 280 is meters squared right now. So you could actually put all the units back into this. And when you get all done, you actually get the unit for this is actually nothings per second. There is no unit, and therefore it's radians. It's not just because I was in radian mode. So that is kind of important to understand, though. I mean, if you're building this and you mixed it up and said that you thought that was degrees, like you broke the machine now, like 4 radians is a lot of degrees. This angle's closing really fast. I purposely made the cable pulling in at 32 meters a second. That's pulling it in really fast. Remember we said L was L was 18. So does it make sense this thing's going to get pulled over here? Well, if it's 32 meters a second, it's going to be like a half a second. And it's going to go bang. And so it's really closing fast, if you will. So all I'm saying is that answer actually makes sense. Done. So for me personally, I kind of circle stuff along the way that I know is important, but I box the final answer And that's just me talking to me, but it's also nice if somebody else is trying to read it, or maybe it's nice for you if you look back at the notes later on. Just a little side note. Just this is interesting. I'm going to erase this, but quick side note. If we were sitting here with cosine equals 28 divided by negative 280, does it make sense to you that that's a right triangle? Cosine is adjacent over hypotenuse, right? It could also be thought of as negative 28 over 280. If it's negative 28, then that would actually put it over here in the second quadrant so that the x could be negative. The hypotenuse is 280. What I really have then is that angle right there. Well, I actually never really wanted to know this. I never wanted to know theta. I wanted to know the sine of theta. So couldn't you figure this length out based on Pythagorean theorem over here? Again, this is the logic of what I showed you with inverse trig identities. But if I said, okay, I can figure that out. What is 280 squared minus 28 squared? Take the square root of that. I either get a decimal, I get the same 278 we got just a minute ago, or I get the square root of 77/16. So does it make sense I could replace the entire sine of theta with the square root of 77/16 over negative 28 right now? And it's still perfect if I had some nerdy reason to be perfect. That's just interesting. I don't really want you to know that. I just think it's kind of cool to point out. I never wanted to know the angle. I wanted to know the sine of the angle. So I never even had to figure the angle out to actually get the answer to this question. Notice in that example, I never knew what the angle was at all. So interesting. So we had an equation, number one, we got it moving, and then we sort of figured out cool stuff. We used the equation to actually, figure something out. That's the pattern of these types of problems. Let's do another example. And again, please interrupt because I'm kind of looking down at my notes. I'm talking. Don't raise your hand. Just immediately start talking if there's something bugging you. Listening to me say this is not equal to you understanding it. Like, you got to process. You got to think.
Yeah, I got a different answer than you, and I'm not entirely sure why.
And it could be because I made a mistake for sure.
Yeah, so I did it just figuring out the overall equation relating theta prime into L, just using substitution. And then when I plug 18 in, I get negative 5.197, not negative 4.1. And I've been running through the algebra trying to see if there's a mistake anywhere, and I can't find it.
You kind of did it different than me, right? So it's not, you're not, in a sense, we're comparing apples and oranges. So save that, and let's see if we can get to the bottom of that after class. I don't want to derail everybody else's understanding. I want to go look at what you did and do and follow what you did and see if you're right, then maybe I made an algebra mistake. If you're not, then let's figure out why not. Let's see. Let's do a question kind of similar to yesterday. And there's one in your quiz like this, which I didn't realize when I was teaching this yesterday, but last period, but let's say you got this car, and this is actually, in terms of a sales pitch as to why this is cool or why you really need to know this or why somebody would need to know this, this might be the sales pitch. And so here's this car. You can tell I'm a great artist now, if you didn't already know. Here's this car ripping by, and you are a cameraman filming this. And so you're over here with your camera trying to aim at this thing. We'll give it an old school camera. So you're filming the car and it's driving by, and we'll say it's going. And again, I don't want to screw us up with units. That's even worse. I could give you miles per hour, and then we have to do everything in feet, like we did with the cop yesterday. But let's just say this car is traveling at 112 feet per second. That's pretty fast. That's a third of a football field in 1 second. So that's not ridiculously fast, but it's reasonably fast. The car's ripping by. And of course, you're trying to film them in the sense that your camera is pointing here, like right as the car passes in front of you. But then the car just goes ding, 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 ding. And so you're trying to, film it up here now. So again, this creates a triangle just like last time. But this is much better because it's a right triangle. So we're not going to have to create near as complicated of a formula this time. So this is a given in the problem. You are staring at this car that passes by in front of you. So that's 90 degrees. And again, I would ask you the question of the 3 lengths and 3 angles in this triangle, which ones are constant and which ones are static? Which ones are, that's the same word twice. Which ones are constant? Which ones are changing? Which ones are static? Which ones are dynamic? Which ones are not moving? Which ones are moving?
The base is a constant, right?
Yeah, you're exactly right. This distance down here would be constant, so I'll give you a number for that. Let's say it's, I don't know, 34 feet. That'd be a constant. What about this length up here, the hypotenuse? Is that a constant?
I
don't think so.
Function is wanting me to say no, because if you're moving your car length further, wouldn't the hypotenuse get longer?
That's right. So at one point it was here, the hypotenuse is short, and then it's here, and then it's here, and then it's here. So yeah, that length is
But don't you have your given angle? So wouldn't that be a constant, like your 90 degrees? Wouldn't that be a constant?
The 90 is a constant. Yep, that 90-degree angle is a constant, but this is going to be a variable again. Again, I'm just using L for length. What about this angle down here? Yeah, that's same reason. That's opening up wider. So that'd be a variable. And I'm not going to write it in, but it's like, well, yeah, I am going to write it in. What about this length right here? Well, that's changing too. So I guess I'll call that C for car. So almost everything in this is changing. The only things that are constant is the 90-degree angle, just because notice there's nothing physical in this problem. It's just the cameraman is 34 feet away from the track and the car passes by in front of him. Now I'm going to write this in calculus just to save a little bit of time. But if this was in a sentence, I might say something like, how fast is the distance between the camera, the distance between the cameraman and the car changing? How fast is the distance between the cameraman and the car changing? Oh, that distance. How fast is that changing? That would be code for find DL/DT. How fast is that changing? It's getting longer and longer and longer. How fast is it changing? In a practical sense, why would somebody care about that? Why would a camera care about how far away something it is from it?
I don't know if you wanted to change the way it's focusing on the thing.
Exactly. You guys live in an era where everything autofocuses, but it's because of calculus that things autofocus. At least calculus contributes to that. I don't know a lot about that, so I'm going to pretend that I do. But that's exactly right. Like for a it used to be, if you will, people actually had to manually focus the camera when that went by, but at least the camera has to be focused. It has to change. And so that's all done kind of automatically now. But that's a very interesting question. Like you got to keep the thing in focus. You've all watched video and you've probably seen it on your phone, how it like has trouble for a minute. Like you turn to something or you're trying to follow it and it's like has trouble for a little bit, trying to figure out what the heck's going on. So the point is that's practical. Like for somebody who's doing engineering, that'd be practical. Second thing that's practical here would be how fast is the angle between where the car passed by and where the car is now? How fast is that changing? That's also practical for somebody with a camera because you have to turn your head to follow it. Or as I mentioned yesterday, even better, could you be the engineer that designed some kind of a robotic system where the camera could follow the car perfectly because it understood the math, because you understood the math? Could you keep the car right in the center of the camera as it went by? Well, you're not going to do very good at that. You're going to be all wobbly and you'll have to rely on your coordination. But a machine could do this really well. So that might be a couple of things we want to find. And let me try to just give you make this a little bit more like maybe a book assignment, is just give you some givens. And so notice if the car was traveling at 112 feet per second, that would be one of the givens. Now they're not going to tell you dc dt equals 112. They're not going to say it like that. They're just going to say the car is traveling 112 feet per second. And you have to understand this well enough to say, oh, well, that means this distance over here is a variable, and I'll give it a name, c, and then that's how I get it into the problem, is saying that, oh, speed, that's a derivative statement. So I can't say c equals 112 because c is a length. C is feet. L is feet. But dc dt would be speed. So that's a given. The second thing that would have to be given, just like in the last problem, is some snapshot in time, because this is moving. So we have to say, if I said how fast is L changing, you can't answer that question until you know when, until you know where the car is. And so let's see, what snapshot in time should I give you? I could make it hard and say after the car is driven by for 4 seconds, but I'll just make it easy. Snapshot in time, we'll give it as c equals 200 feet. When c is 200 feet. And again, you got to understand, c is not permanently 200 feet because the car can't be 200 feet away and moving at the same time. That's a snapshot in time. A billionth of a second later, it's not 200 feet. This is just when I decided to pay attention. As I said before, it's kind of like me asking you, how much have you weighed in your life? And you'd have to say, well, when? Like when I was born, I weighed this much. And when I was 12, I weighed this much. When? And that's the same thing here. How fast is the angle changing? Well, when? It's different every time. That's what we saw yesterday. How fast are you going according to the cop's radar gun? Well, it depends when he pulls the trigger. So we got to have a snapshot in time with these problems. I think that's all the givens you would need. Okay, so to get, let's first get, since I put them in order, let's first try to get dl dt. Again, for now, you are ignoring this second question. That's not there yet. I'm just answering one question. Just pretend that doesn't exist. We'll get to that in a second. What is my equation? What equation do I need? Well, the rate that I know is 112 feet per second. That pertains to c. So I need an equation with a c in it in order to relate the two rates. And because I'm being asked for dl dt, I need an equation with L in it. So I need an equation with C's and L's, and ideally nothing else. I can get an equation with C's and L's by saying, let's see, the sine of theta equals opposite over hypotenuse. There's an equation with C's and L's, but that also gets theta involved, and I'd like as few letters as possible. I really would like not to have theta in it. What's a better equation?
The Pythagorean theorem.
Pythagorean theorem. Best equation here would be to say that 34 squared plus c squared equals L squared. That's better. It's less trouble.
I have a question.
Good.
Could you just solve for cosine or sine and use that, because wouldn't that solve for both your theta and your unknown L?
And are you saying that for when c is 200?
Yeah, or you could just solve the equation leaving c out of it, like just leaving c as a constant, solve for that, and then you could place in either when you have a theta snapshot or a c snapshot.
Yes, but you got to be careful because c being constant contradicts the speed of the car being 112 feet per second, because c is not always 200. That's just a snapshot in time. So if you use C as 200 and you go in and solve for theta and solve for L, you got to realize that only applies for that snapshot in time. And so we really need an equation that's still moving. And then this Pythagorean theorem equation is still moving right now. I haven't put 200 in for C yet. And the reason for that is because I need to take its derivative, because my question in this problem was, I'm interested in the speed, not the length. So in Math 112, they could have said something, they could have given this whole same problem, and they could have just said, when C is 200, how far is the cameraman away from the car? And then you say, oh, that's a static problem. I'll use this Pythagorean theorem down here, and I got my answer, I'm all done. But a second question, like what we can do as calculus students, now that we know math a little more deeply, is we can talk not just about the lengths and angles, but we can also talk about the speed at which those lengths and those angles are changing. And so there is more than one way to do this, for sure. I'm trying to show you, in a sense, the most logical, easiest way. But you're more than welcome, Eve, to get all the letters involved you want and take the derivative. Absolutely.
Okay.
So again, I'm just circling important stuff. So here's the static equation, in the sense that if I know C, I know L, and later on I'm going to probably need L, in which case I'll put 200 in for C and I'll get L. Maybe I'll need it, I don't know. But now I got to get this thing moving. So if I get it moving, then I'm going to take the derivative. Well, 34 squared is a constant, so the derivative of that is gone. The derivative of C squared is 2 times C times the derivative of C. The derivative of L squared is 2 times L times the derivative of L. And this is the equation I've been after the whole time, because I was interested in the speed of things. And now I've got an equation with speed. I've got two equations. They're both great. One static, one dynamic. So I teach engineering, winter and spring. My winter class is called statics. My spring class is called dynamics. Those were basic required engineering courses. A lot of you mentioned you're in that program. I'll probably see you in there at some point again. An entire class devoted just to things not moving, and an entire class to things moving. Like, this is a really important concept. So they're both good. They're both awesome. You just have never known about the second equation until calculus. Stuff does move. If there's a backhoe at my house, I hope it's moving, because it's on the property to dig holes and put a pipe in and stuff. Like, let's get moving. Let's get stuff done. All right. Now I can figure stuff out. So I'm interested in the second equation. And then I look back at my givens and I say, hey, I was given the fact that dc dt was 112. And so I can throw 112 in for dc dt. I think that's going to go off the page. I'm going to make this shorter. And let's see what else I was given. C was 200. That's cool. Glad to see that. And of course, this is what I'm being asked for, so I'm not going to be given that. They were asking me, or the problem's asking me, for how L was changing. And so it is asking me for L. Like, that's the one variable that I wasn't given. But as I said a minute ago, now we go back to that static equation. When C is 200, I can solve for L. So 34 squared plus 200 squared is a big number. And if I take the square root of that, I get 202.86, call it 202.9. So this spits out 202.9. And so now I know that. So now I know everything I need. I got an algebra equation. I had an algebra equation with 4 unknowns in it. I was, in a sense, given 3 of them, and now I can solve for the last one. So I know how fast the car is going away from me as far as the camera is concerned. Remember, the camera doesn't care about anything, but just how fast is the car going away from it. If you're going to get the autofocus thing to work, you got to be able to figure this out. So just to give you time to process, I'll plug all this in. So 2 times 200 times 112. I can't type. 2 times 200 times 112 is 44,800. So I get 44,800 equals 2 times L. 2 times 202.9. Don't want to screw up, so I'm not going to do it in my head. That equals 405.8 times dl dt. And so all I got to do is divide 405.8 over to the other side. So that's easy. So I do that and I get about 110.4. So dl dt. What would the units of this be? I hope your homework assignment, they ask you for that. This is the kind of thing I would want on a test. I mean, this is all great, but if you don't know what the units of that are, then you're not building the camera here. Like you got to know the units. Since L was a measurement in feet and time was in seconds, this must be feet per second. For those of you that are a little sharper and you're taking physics, you might try going back and not leaving the units till the end. Like go put the units in this the whole time. So I'll just talk about it really quick. This is 200 feet. And this is 112 feet per second. So this is feet times feet per second. So this is feet squared per second on this side. And the same thing would be happening over here. Like the units you don't have to reason the units out yourself. You could just leave them in the problem. Don't put the naked numbers in there, leave them in there and it'll actually come out fine in the end. That's not as important with this problem because it's dealing with length. But the second problem where we say, okay, now let's go back and see how the angle's changing. Let's get the automatic feature of the camera following the car. Let's see if we can get that figured out now. So let's go blue. This was find dl dt. Now we're talking about the speed of the angle. And it's kind of like what we just did a second ago. We found the speed of the angle of that boom lifting up that box. So again, what I'm really trying to do is relate dc dt, trying to relate dc dt to d theta dt. So does it make sense that I need an equation this time with ideally c and theta? That's what I really would like, is an equation with c and theta only. Now, since I know a whole bunch of stuff about L, it actually wouldn't be the end of the world if L got in this problem too, because I know a bunch of stuff about L now. But ideally, I'd really just like c and theta. So what equation in this right triangle would just get c and theta involved?
Law of sine.
Law of sines will do it. But this is a right triangle, so you could do an easier equation than the law of sines. In that previous problem, it wasn't a right triangle, so I had to use the more complicated trig version of the law of sines. But how could
just
you
use tangent?
Trig? Yeah, because this is a right triangle, tangent of theta is opposite over adjacent. So tangent of theta would be c over 34. That's easier than the law of cosines. But I want to qualify this by saying law of cosines works just fine. It's just messier. You could even use the sine of theta, which is c over L, because you know about L. So even though it's going to have L's in it, you got answers for L now from the previous question. But it's easier if you can just stick with the letters that you know. Well, we know this one, this was our given speed, so we got to somehow get c in it. And then we want to know something about theta. That's why it's got to be thetas and c's. This is very challenging. So let's see, thetas and c's. All right, that would be the tangent of theta equals opposite, which was c over adjacent, which is 34. I don't care if 34 is in it because that's a constant. So that doesn't trouble me at all if there's constants in it. I just don't want letters in it. So there's our static equation. But again, why do we even come up with this equation? Well, we came up with it because we need to take a derivative to get it moving, because that's what we really want to know about is speed. We got to have an equation if we're going to take its derivative. So now we can take that derivative. Now, from our discussion in 3.1 about inverse trig, would you mess with this first? Like, if you said, I think I'm going to solve for theta, so now I have the inverse tangent of c over 34. Maybe you decide I'm going to do that, and then I'll take the derivative. And my note sheet tells me that the inverse tangent of junk is 1 over 1 plus the junk squared or something like that. I find myself thinking, I don't like inverse tangent, it's weird looking, and I don't have to rely on the formula sheet. I'd rather just take the derivative of tangent just like it sits. But they both work, and actually, this one down here would be faster. Like if you use the note sheet, that's actually faster. But don't be afraid to think. I mean, it's a lot to ask when you're first learning this. Just to even survive these questions is hard. But remember, you can do stuff. Or maybe you don't like the fact that there's a 34 there. Can you multiply both sides by 34 and then take the derivative with 34 on the other side? Just because it's less confusing to you? Yeah, it's probably a good idea. But now I'm going to take the derivative and get stuff moving. So what happens if I take the derivative of tangent of junk? I learned a long time ago, you say that the derivative of tangent of junk is secant squared of junk. I also learned from the chain rule that it's times the derivative of the junk. On the other side, I have 1/34th times c. It's just a constant, 1/34th times c. The derivative of a number times a constant is just a number. So the derivative of 1/34th times c is 1/34th times the derivative of c, which is not 1 because we're not taking the derivative with respect to c, we're taking it with respect to time. So the derivative of c is dc dt, and the 1/34th comes along for the ride. Actually, I'm not going to circle that just yet. That's kind of ugly to me. Like, I don't want to use that. I don't like the 34, and I don't like secant squared. It doesn't have a secant squared button. So let's mess with this a little bit. Like, couldn't I multiply 34 over to the other side? Let's go blue. Couldn't I multiply 34 over to the other side? And let's just do this in our head. Isn't secant 1 over cosine? Because I really would rather have a cosine button on my than a secant. So it's 1 over cosine squared. But then I could multiply both sides by cosine squared. And so then this is what would be on the other side. All I'm saying is I think I like this equation better. I feel like I don't have any fractions. I have a cosine button. I'd rather work with that one than the green one. Doesn't matter. They're both fine. Again, interrupt. So this is the equation I want to plug stuff into. First of all, it gives me a place to plug the speed into. We were told in this problem that dc dt was 112. Maybe I will leave the units in this one, feet per second. And let's see, there's a theta, and there's d theta dt. Of course, I'm not going to be told d theta dt because that's what we were trying to find in the first place. So if you will, this recipe is calling for the cosine. Well, that's a bummer because the snapshot in time I was given was when c was 200, right? That was my snapshot in time. So it's like, dang, there's no c down there. That's disappointing. So what am I supposed to do? You tell me, what am I supposed to do? Like the one thing that I know.
Can't you plug the 100 on the C on the static equation and then find the theta?
Exactly. That's a pattern we're seeing kind of every single time. In other words, that C right there being 200 allows me to find. And again, if you want to be really cool about this, you already know the tangent of theta is 200 over 34. So wouldn't that mean if this was theta, then this is 200 over 34? And we don't really want to know theta, we want to know cosine. Cosine is adjacent over hypotenuse. Couldn't you use the right triangle and find the hypotenuse and skip knowing the angle altogether? You absolutely could, but I'm just going to do this kind of slowly and a little more carefully. So let's see, the tangent of theta. If the tangent of theta equals 200 over 34, and I take the inverse tangent of 200 divided by 34, second tangent of 200 divided by 34, I get 1.4 approximately. So theta is approximately 1.4. Great. Now I can put 1.4 in there. I'm good. Incidentally, This is a little tricky, but think about this for a second. Let's see, where was that 34? What was that 34? Where'd that 34 come from? Tangent of C equals over 34. Oh, that was feet. So this 34 over here is actually feet. That's interesting. So that's 34 feet. What's the cosine of 1.4? What's the unit of that? Not 1.4. 1.4 is radians, but what's the cosine of 1.4 radians? Well, remember, cosine means this side, 34 feet, divided by this side, let's say it's 202 feet. Cosine of this angle right here is feet divided by feet. It's unitless. Once you take the cosine of it, there's no unit there at all. Again, I'm saying this for you physics people, so maybe you get a little better at physics. So you end up with no unit here, and this unit is feet per second. And then over here, dt is seconds. So in order for this to be feet per second, this has to have no unit, which means this is radians per second. Like no matter what you do, the answer to this is radians per second. You don't have a choice. You can't make it feet per second or degrees per second. That's just interesting to point out. Ignore what I said if you're not a physics person, because this is already painful enough. So awesome, I'm home free. So I have 34. Let's continue in blue. I have 34 times d theta dt equals the cosine of 1.4. Cosine of 1.4 is 0.17, and that's squared, times dc dt is 112. So I just need to divide 34 over to this side, and there's my answer. So 0.17 squared times 112 equals, divided by 34 equals 0.095, approximately 0.1. d theta dt is approximately 0.1 radians per second. Weird. The language of the universe for angles is radians, not degrees. I did not understand that for a long time in my math career. The whole radian thing just really didn't feel good to me. Again, I still don't think in radians. I find myself wanting to convert that to degrees right now by multiplying by 180 over pi, just because if I'm thinking of myself as the cameraman, I don't think in radians. That's not my native language. So if I multiply that by 180 divided by pi, and I get 5.5 degrees, I think, okay, it's moving at 5.5 degrees a second. But remember, that's only at the snapshot of 200, when C was 200 feet. If we had a different one, and that's what we saw with the COP problem yesterday, we'd get a totally different speed. So we won't do another snapshot in time than 200, but that's just interesting to point out. So irrespective of, like how much you're suffering trying to understand this, at least I think you can see with this question that this has got some practicality to it. I mean, this is how we have many of the inventions in our culture we have, is the ability to understand how changing one thing changes something else. Just a quick side note, in an intuitive sense, we actually do calculus all the time. This last weekend, I was on the river in my raft. And so here's this rock, and the river's flowing this way. And here's my raft, and I'm heading toward this rock with my oars out the sides. And I see myself going toward this rock. And so what do? Well, I start paddling faster. Like the faster the rock comes at me, I look over and I say, how fast is that rock coming toward me? Whoa, that rock's coming really fast. I better paddle faster. Like that's intuitive calculus. People are doing calculus always, all the time. They just aren't actually doing the math. If you see the car in front of you and it stays the same size, then you say, oh, the car's going the same speed as me. But if the car starts suddenly getting bigger, then that means the car's stopping. And then you start pushing the pedal. Hey, the car's getting bigger. I better push the pedal. And if the car gets big really fast, then I better push the pedal really fast. Like that's intuitive calculus. One thing changing causes something else to change. We're doing this all the time. It's just that, what I'm showing you here is a little easier to assign numbers to, and also kind of a little bit more engineering related. right, let me show you one more cool problem. I think it's kind of a neat one too. I mentioned the other day going out the door, like the sand in the hourglass, kind of a problem. So let's call this the sand pile problem. So if you have a conveyor belt right here, and sand is on the conveyor belt, and it's falling off of this and landing in a pile down here on the ground. You probably have a sense of this. Well, it's going to land there in a pile. But what's that pile going to look like as time goes on? It's not just random. It's actually a very geometrical shape. What does that look like as you let the conveyor belt run?
A cone?
Yeah, a cone. Again, you don't need to know that to get the problems right that I'm doing here. But in the end, this thing is going to be a cone. It's going to be a real symmetrical cone. So we're saying this is sand coming off of this. And so would you agree there's a relationship between how much sand is falling off the conveyor belt and how fast the pile's growing? If the sand is coming off the conveyor belt really fast, then the pile's going to grow really fast. If the sand's coming off really slow, then the pile's going to grow really slow. There's a relationship between these two things. Let's see if we can put numbers to that, quantify that a little bit. So, and again, I'm going to try to give this a little bit more like a little bit more like a textbook. I'm trying to teach for understanding, but I'm going to try to give you all the givens right off the bat. Given the sand, and I'll just kind of abbreviate. The sand is 40 cubic feet per, let's use a different time unit, minute. 40 cubic feet of minute or of sand are sort of falling off that conveyor belt. That's given. And we'll say that the snapshot in time is when the pile is, let's say, 12 feet tall. And let's say, can you find how fast the height of the pile grows? How fast the height of the pile grows? Can you find how fast that's growing at the snapshot in time when the pile is 12 feet tall? Notice there's no letters in this anywhere. Like you got to add them yourself. That's why these questions are really hard. You can see there's a relationship between these, but it's like, how would I conceptualize that? Well, let's just get some letters involved. Let's add to our graph or picture a little bit. Well, how fast the height of the pile grows? Well, if that's the case, then don't I need H for the height of the pile? And again, it makes sense that it'd be H, not 12, because if it's 12, then the conveyor belt's turned off. You see what I'm saying? You can't just put 12 over there. That's what's tricky about these questions. 12 over there contradicts 40 cubic feet per minute. So this statement here, this question is sort of code for find dH dt then. That's what I'm trying to find. And so again, I think, oh, okay, this is a derivative problem. This is a problem where I need an H in an equation and I got to take its derivative. And how am I going to get 40 cubic feet a minute involved? Man, that seems complicated. How do I stick that in there? What is that?
What's the equation for the volume of this thing?
Yeah, good question. We'll get to that. Equation of a volume of a cone, I'll write it down here. You'd have to look this up. Is 1/3 times pi times radius squared times h. You've probably seen that equation before, but it's very unlikely you have it memorized. Do you agree that this statement right here is a volume, 40 cubic feet. And that statement is time. So this is really code for dV/dt. So basically what I have is this dV/dt, which is a constant of 40 kind of falling off the conveyor belt. And so what this tells me then is I'm going to need an equation with H in it and V in it, because a change of volume was given to me. So I need V in it, and I'm interested in or I'm being asked about the change in height. Notice you could be asked about the change of radius, because isn't the bottom of the pile growing as time gets on? So I could ask you about dr/dt, the radius of the pile. That'd be interesting. So I need an equation with H and V, and I think it was either Felix or Caesar that asked, what's the equation for this? Well, this is the only equation I've got right here, but unfortunately it's got R in it. You see, that's not good. I don't know. That's not good at all. If I take the derivative of this right now, which you absolutely can do, you get a dV/dt, you get a dr/dt, and a dH/dt. And also it's R squared times H, which means you got the product rule. So it's kind of cool that you can take the derivative of it right now and get all the stuff involved. But because it would have a dr/dt in it, does it make sense? I wouldn't know what to do with that. So it feels kind of confusing. Well, it turns out I'm going to give you one more given here that I sort of purposely left off earlier. And I'm going to make this realistic. Look this up on your phone right now and tell me if this isn't true. It turns out when sand falls into a pile, it finds an angle according to the sand. Like if it keeps piling up on top, it'll sort of slough off. If I remember right, that angle right there is around 34 degrees or 32 degrees or somewhere around there. It's called the angle of repose, R-E-P-O-S-E. This is a fact of science, if you will. When rocks break up on the top of a mountain, they'll actually form an angle on the side of that mountain, and that angle is predictable just because of how friction works on rocks and so forth. Angle of repose of sand. It'll probably say something about whether it's wet or dry, because things are stickier. It can actually stack up steeper if it's wet than if it's dry. But that angle's around 32 degrees. If one of you looks it up on your phone and it's not, tell me and we'll change it. But again, I want to make this realistic. And so that's actually a third given here. And your book won't give you a problem that's kind of weird, this kind of hard, or I should say realistic. Angle, I'll just say angle is 32 degrees. The other thing I could say is something simpler, like the height is twice the radius. I could say something like that. The height is twice the radius. So that means you'd have to double the radius to be equal to the height. I could tell you that too. Or I could just tell you the pile is 12 feet tall and the radius is 4 feet tall or something like that. But the point is, this has got an R in it, and this time you're not getting rid of it. There's no way to get rid of that. I can't come up with an equation with just V and H in it. Well, if the angle is 32 and this down here is the radius, then does it make sense you could say that the tangent, since this is a 90-degree angle, the tangent of 32 would be equal to opposite divided by adjacent? And therefore I could say that R is equal to H divided by the tangent of 32. That's extremely cool, because what that means is I could take that and replace it in this equation right here, and then I wouldn't have R in it anymore. That'd be nice. So what's our equation? V equals 1/3 pi, or I think I'll write it as pi over 3, times R squared, but we just got done saying that R could be replaced with tangent, H over tangent of 32. R is still squared though, times H. But I'd like to clean that up a little bit. Like I don't want H squared and H in it. I don't want to do that as though it's a product rule. So, and then here I have pi divided by 3 and then tangent of 32 squared. So just to make my life easier, tangent of 32 is just a number anyway. I'm going to type pi divided by 3 divided by the tangent of 32. Notice that's 32 degrees. I just realized I got to switch my calculator mode 2 degrees because that doesn't say 32 radians. So pi, I'll go fast here, clear. Pi divided by 3 divided by a parenthesis tangent of 32 squared. So that decimal is 2.68. So I get 2.68. And again, I'm rounding it, so I think I'll tell everybody that it's approximate. And that's now just h cubed. So I took pi divided by 3 divided by the tangent of 32 squared, and then it's h squared times h. And so that's a much easier equation to work with. If you're a person a true mathematician that likes perfection, leave tangent of 32 in it. Just say it's squared. Didn't hurt anything.
For like textbook purposes, they would have to give us the angle of repose or like the radians. Yeah, we wouldn't just have to try to figure it out.
That has to be given, yeah. Like I just wanted this to be a little bit realistic to you, but a textbook would never say this because math people don't even know stuff like that. Only science people know stuff like that. They would say, and also given that the height is twice the radius or something like that, they'd have to give that to you.
Okay.
It's a good question. So I've got my static equation. Now let's get that thing moving. And again, why are we getting it moving? Because we don't care about h and v, we care about dv dt and dh dt. So let's get it moving. So the derivative of v is the derivative of v prime, dv dt. The derivative of h cubed would be, well, hey, this is a power rule problem. So the 3 comes down front to be multiplied by 2.68. 3 times 2.68 is 8.04. And then the power reduces by 1, and then because of chain rule times dh dt. There's my very satisfying dynamic equation. There's my dynamic equation. And again, the dynamic one's the one I'm interested in. That's the one that's got stuff moving. Notice it's got 3 unknowns. It's got dv dt as an unknown, it's got h as an unknown, and it's got dh dt is an unknown. So since I'm being asked for dh dt, then I must be able to figure out, or it must be given to me, what h is. I must know what h is, and I must know what dv dt is. dv dt was given, forgot what it was, 40 cubic feet a minute. And again, I'm going to leave units off, but you could pay attention to that here and it would work. 40 cubic feet per minute. This h is feet, so that'd be feet squared per minute times feet per minute. Feet cubed per minute equals feet cubed per minute. The units work. Was I given h? Oh, thank God. The pile is 12 feet tall. The thing that I needed is the thing that I was given. That was lucky. So the snapshot is h is 12. Good. I just throw h is 12 in. I didn't have to work that hard. I didn't have to use h to get something else. I got lucky. And now it's pretty easy to solve. So 40 equals 8.04 times 12 squared. 8.04 times 12 squared is 1157.76. Just giving you time to process. So if I take 40 and divide by that, I get my answer. 40 divided by 1157.76 is 0.03. That seems really slow to me. dH dt is approximately 0.03. H is feet, time is minutes.
I have a question.
Yeah.
Why did you divide by 40?
I divided 40 by 1157.
Okay, sorry.
Not 1157 divided by 40, which would be easy to screw up. Notice the pile's not growing very fast. That actually feels really slow to me. I should be looking back to try to figure out if that makes any sense. Maybe that does make sense. I mean, the pile's 12 feet tall. It's a pretty tall pile, and 40 cubic feet is quite a bit of sand. But in 1 minute's time, that sand is going to have to pack all the way down all the sides of this, and so it isn't really going to get that much taller. Maybe that does make sense. But I'm always trying to illustrate sense making to you. Like, do you stop and think, does that make sense? I think that's an important thing to do. In your case, you should kind of think, well, I don't know, I hope that's right. Because it's kind of hard to check your work with these problems. As I said before, like this should hurt your brain. Like you actually have to know everything you've ever learned about algebra, like all these geometry formulas. And notice every time we bring some equation in, we have to come up with it ourselves. That's a lot to ask. And then we have to take a derivative, but we're not exactly sure, when to take the derivative and, what different rules might be involved. Notice all the derivative taking we're doing, though, is actually pretty small. It's not like you end up with sine of x to the x power. The models we have for how volume works or how right triangles work are pretty simple equations. So the actual derivative taking is not too terrible as long as you understand implicit differentiation. And the derivative of h is dh dt. But it's like you got to be able to write your own equations. Man, this is tough stuff. This is a culmination of everything you've ever learned in math. And so if you find this hard, you're not alone. All calculus students facing this topic down have some trouble with it. This is difficult. This is one topic in calculus that I actually am still getting better at teaching, even though I've taught for 25 years. Most things I'm not really getting any better at. Maybe I come up with a better example or something, but anyway, I won't ramble more about that. So what I would recommend you do, let's see here.